Hello viewers, welcome back to another video. In this particular video, I am going to address the topic of random vibration. You would have heard the term random vibration or random testing for a particular hardware n number of times. But have you really understood what is random vibration and how random vibration is different from the conventional types of vibration problems that we see in textbooks, especially in the initial portion of the mechanical vibration topic? If you don't have very confident answers for these questions, then this is the right video for you. In this particular video, I will be describing random vibration completely from a descriptive point of view. I won't be using very hard mathematical formulas, but from a conceptual point of view, how it is different from other types of vibration problems. So let's get started. Any particular vibration problem can be thought of as computing the response of a mechanical system, as shown here, when the mechanical system is excited or when the mechanical system is subjected to a particular type of excitation. Mechanical system can be anything. It can be the hardware that you have designed. It can be a payload of a particular satellite, or very simply in a very simplified case, this can be the mechanical system can be this particular cantilever also. Excitation can be thought of as a point force acting on it. Now what is the response? How is this particular beam going cantilever going to behave when it is acted upon by an excitation force? That's constitutes the whole subject of mechanical vibration. Now, depending upon the type of excitation that this particular system is subjected to, there are different types of vibration. The first one, if the excitation force is harmonic, then we have it like this. If the excitation force varies harmonically with respect to time, then we call it harmonic vibration, and we have techniques to solve that. This is another example where your excitation force is not harmonic but it is periodic. In this case, in these two cases, your excitation force is aperiodic, so you don't have a time period. But even then, using techniques like convolution integral, we can compute the response of our mechanical system against this kind of excitations. Keep in mind, in all these four cases, we have a very explicit representation of the forcing function in terms of time. This is also called the impulse excitation. To reinforce your understanding about different types of excitation, I have a few examples with me in which types of excitations will be different from one another. So I will ask you to identify what kind of an excitation will be seen in each of these examples. Let's start with this example of a washing machine. In washing machine, let's say there is an eccentric mass. Due to the wrong distribution of the clothes, there is a eccentric mass which is little m, and it is located at a radial distance of capital R, as shown here. Now, when the machine is operating at an angular velocity of omega, as shown here, this is the equivalent mathematical model of the washing machine. Once this is in operation, then the whole system will be subjected to a force in the upward direction. Pause the video, and what will be the magnitude of the force? Magnitude of the force will be mr omega square, and since this angle is omega t, the component in the y direction will be mr omega square sine omega t. So this is the excitation force acting on the system. Now if we plot that particular function with respect to time, this will look like this. So this is an example for harmonic excitation, where the excitation force is a harmonic function with respect to time. And see, we know everything in this particular expression. Little m we know, capital R we know, omega square, the angular velocity of the particular machine, that too we are aware of. So this excitation function is completely known and it can be written as an explicit function of time. Now go to the next example. In this particular example, we have a cam like this. So this will impart a particular motion to this spring, which will in turn affect the external force acting on this particular mass. Because since this particular spring is seeing a relative displacement of x of t minus y of t, the force acting on that particular mass will be k times x minus y. Since y is following this kind of a trend, the force excited on this particular mass will also follow a similar trend. See, so the excitation function will be following a trend more or less like this. What does this imply? This kind of an excitation is periodic but it is not harmonic. Then we will use techniques like Fourier series to compute the response of this particular system or this particular mass against this type of an excitation. So this is an example where real life example where we will have no periodic but not harmonic excitations. A good example is the engine valves in an IC engine. The last example I have got is an interesting one. Usually jet engines are prone to bird strike. Once the bird strikes the engine, it can cause severe vibration inside the engine and to the connected structures as well. So usually in jet engine design they do consider all these effects and select a mount stiffness, this particular stiffness accordingly, so that a bird strike won't cause much of a disturbance or much of a problem. So in this scenario we call the type of excitation as impulse excitation. So when the bird strikes, it strikes for a very small amount of time, but it will impart a lot of energy. That energy will be related to the mass of the bird and the velocity with which it is hitting. So this is an example for impulse excitation, and using techniques like convolution integral we can solve or we can compute the response of this type of excitation of the mechanical response of the mechanical system against this type of excitations. Again, keep in mind we are completely aware of the amount of energy that goes into the system, because we know the mass of the bird, we know the average velocity with which a bird can hit the your jet engine. So all these things are known. Having seen these three examples, now let's go into the topic of random vibration with another example, and let's see how that particular example is different from the rest of the three examples that you have seen. That was a lot of introduction, but I believe that we we should know why random vibration is special. For that I thought those few examples are really necessary. So in this particular example I have an aircraft. So what I'm interested in is, this is the mechanical model of the very simplified mechanical model of the aircraft. So I have wheels here. To me, in this particular scenario, my interest is on the displacement that this particular wheel will be feeling when it is landing. Okay, if you have ever been on a airplane, you know the process of landing is not that very smooth. It will be, it can go wrong at times. It's a very complex process. So what I did, I put some kind of an instrument and I started measuring the displacement of the wheel with respect to time. Okay, so then to much of my interest, the displacements were very random. Okay, this was not random, just like going all over the place. The curve was going all over the place. Okay, well and good. I thought I did the same kind of test or the same kind of experiment where I measured the displacement of the aircraft the next day also. On the first day, I got some kind of a curve as shown above. Then I repeated the same experiment on another day. Then again, I got another curve which is something like this. Okay, this is again x2ot. I will say since it is the second day and with respect to time. Then I repeated it on the third day also. Then I got another curve. I will call it x3 of t, which was looking somewhat like this. Okay, clear? Now, having seen this, what are the differences you think? In the first case, when we had harmonic or periodic excitations, everything was deterministic. We knew the amplitude of this curve, we knew the time period, we knew how much of energy that goes into the system, what is the amplitude of the excitation, we knew everything. But when it comes to the example of the aircraft, the displacement of the aircraft is completely random. It is changing from one day to the other. Why is it so? Hold your thought and come back. The main reason for this is that there are too many variables in the example of a aircraft landing. Too many variables. For examples, the wind conditions on that particular day will have an effect on the displacement of the aircraft. The tire pressure will have an effect on the displacements of the aircraft wheel. Similarly, the temperature on that particular day and the type of landing, whether it was a smooth landing or a rough landing. So, the main reason for the variation, for the very wide variation in the behavior of x of t with respect to time, is that there are too many variables involved in this case. But when it was a washing machine, there were only few variables. We clearly understood what are the variables and we were able to come up with an expression for f of t or the excitation very precisely in terms of time. But in this case, f of t is dependent on too many things. There are too many depending variables or dependent variables, so that we can't have a very explicit description of the forcing function in terms of time. So this is not deterministic. This case, the excitation is not deterministic. Now, what is the way ahead? That's the next question. So each day we had each curves, like we had x1 of t, which was, then on the second day we had x2 of t, then we had x3 of t. Each day the response of the displacement of the aircraft wheels were different, and they were very complex. If you remember, they were very complex like this. So one technique is, now you know what is the x with respect to time. Can you compute the response for each of these functions? Like this is x2, this is x1, this is x3. That's one idea. Let's say I compute the response for this function, I compute the response for this function, I compute the response for this function separately. Then for each of these excitations over here, I will have three different responses. Let me call it y1 of t, y2 of t, y3 of t. This is not practical. This is not going to be practical, because each day this is going to vary and each day I will have a totally different response. Now, how I will characterize the system? That is going to be complex. So this particular idea won't work because there is too much of data to handle. I do a similar kind of observation for 50 days, then I have 50 excitation functions as shown here, then I will have 50 responses. How to conclude, how to take meaningful conclusions out of it? It will be really difficult. So the method we usually incorporate in random vibration is that we won't work with the time description of the responses or either the excitations. We will describe the excitation in terms of some averages. You make sure that you heard me correctly. We will describe the excitations and responses in terms of averages, and we expect that some statistical regularity in this, some kind of pattern in this data. Like I take this kind of functions for 100 days, then I'm expecting some kind of statistical regularity. Then you can ask me, what is statistical regularity? But to tell you very briefly, you take some averages of the data, and when there are so many samples, these averages are tending to meaningful values, then you can say the data is exhibiting some kind of statistical regularity. Let's say I take one average and I take 100 examples and I compute this average, then I take 200 samples, then I take this average. These two averages are more or less the same. Then you can say, okay, this data is showing some statistical regularity. So, if the excitation is showing some statistical regularity, then we can say, or then we can describe the excitation in terms of averages, taking the same to excitation. Since the excitation is having some kind of statistical regularity, the response will also have some statistical regularity. So response also will be described in terms of averages. That's how we work in random vibration. Now what are the different averages we talk about in random vibration, and how we make sure that the response is having some kind of statistical regularity? All these things will be discussed in the later videos. Thanks for watching.